So, let us continue the discussion on Pulsejet engine. Now, we have started looking at the aerothermodynamical analysis of different engines. So, we started with Pulsejet and then we will move to Ramjet and Scramjet before moving into the engines like turbojet or turbofan, where you have the rotating component. So, the biggest difference between this Pulsejet, Ramjet or Scramjet engines with the other section of turbojet or turbofan is that whether it is a non-rotating part, existence of the non-rotating part or the rotating part. And the one which we are now discussing, like the Pulsejet or Ramjet, they do not have any rotating components like compressor, turbine. So, that is the advantage. So, it is a geometrical configuration which does the compression along with the diffusion, so that the proper flow rate can get into the combustor. So, this is what we stopped for the Pulsejet. Now, the one which we go of looking at the pulse detonation engine, and we have since the different approach of the pulse detonation engines. So, this makes a new approach towards non-continuous combustion. They are also very easy to manufacture, that is obvious, and also having higher fuel efficiency compared to turbofan engines or something like that. Now, so actually to date no practical PD engine has been put into the production, but several test bed engines have been built by Pratt & Whitney, General Electric, that have been proven the basic concept. Extensive work which has been carried out or being carried out in different NASA center, but theoretically it can produce an engine with the efficiency for surpassing the gas turbine with almost no moving parts. Probably this is an futuristic engine what could be used. Now, the difference between regular jet engine, where the regular jet engines the operate on a deflagration of the fuel, deflagration of fuel, that is rapid but relatively gentle subsonic combustion. But in pulse detonation engine, it is concept of active development to create engine which operates on the detonation of fuel, detonation of fuel. So, it is based on the detonation mode. So, now, so this is what the nature of a pulse detonation engine, which one can look at it. So, when we are talking about this pulse engine, so this portion is not there. So, this is a typical nature which is also possible for pulse detonation engine, and now this can be classified into pure standalone, which is standalone, which could be combined cycle and hybrid turbo machinery cycle. Okay. So, the pure one which could be based on the pure detonation tube, and the other ones are the combined one. So, which can be, now one can look at how this process can go on, like we have a chamber, let us say this is what, and this is a closed valve condition, let us say closed valve. This is the detonation front, this is reactants, this is open end. Then in the second phase you could have where the products here, and this is the situation where you have this is B Taylor wave, this is again detonation front, and you will have detonation speed. Now then you could have like the front going this side, this is the first reflected characteristic. Then you can have which is going like this. So, non-simple region, which is non-simple region, and then so this could be product or air interface. Now then you can go to completely like this, where this is brand product, then you can now have like this is product, this is shock wave, now this is open valve, air coming in. So, this is the air and product interface, or again it could go like this, where this is the thing, so this is reactant, this is air, reactants air interface, this is air product interface, and this could be product air interface, and these are the shock waves and all this. So, and other cycle pattern could be like this, where you have this is air, this is reactants. So, these are reactants air interface, this is air product interface, and or so this is again closed valve, this is completely reactants, this is again reactant air interface. So, you can see different sequence. So, unlike the Pulsejet combustion in PD is supersonic, effectively an explosion instead of burning, and shock wave of the combustion front inside the fuel serves the purpose of shatters the valve Pulsejet. This is also can be looked at that. Now, the other one is that we said pure PD engine. So, that is array of detonation tubes and nozzles. So, pure PD, this has array of detonation tubes and nozzle. So, the application primarily is in military application, because they are light and easy to manufacture and have higher performance around Mach 1 than current engines. So, another thing is that when you go to that range, basically the noise and there is a drop in efficiency at higher Mach number. That is why when you increase the Mach number, this is not very often desired solution for the higher Mach number application. Now, the combined cycle PD is provide the most exciting possibilities for an aviation. adding a PD to a flow path of ramjet or scramjet would make the engine capable of operating between Mach 5 or higher. Or you could have hybrid PD which use the detonative combustion in place of constant pressure combustion, usually combination with turbo machinery. So, this could be also again two types. There are different, could be hybrid turbofan PD, or it could be, the one thing one can look at it is that when you go by the Mach number, let us say this is 1, 2, 3, 4, 5, and this is ISP or specific impulse, let us say 1000, 2000, 3000, 4000, 5000, then this goes like this. These are for the ramjet for different fuels. Now, at the same time your PD engine will be like this. This is for H2, this is with JP10, then this is H2, this is JP10, like that. So, this is how. Now, in hybrid turbofan PD, that we will have a look at that while we are talking about the turbofan engine and with this kind of discussion. Now, we will move to ramjet. So, that is the, so it is another type of engine which was first proposed in 1930 by 13. So, it may be either subsonic or it could be supersonic. But one of the biggest problem is that with the ramjet, the thing is that in the ramjet it depends on the compression of the incoming air through its geometric modifications. So, it cannot develop static thrust. That is one of the issue with this. The vehicle must first, therefore, cannot from the standing it cannot start. So, it has to be accelerated by other means to reach a sufficiently high speed, and then the ramjet could be in operation. But although the ramjet can operate at subsonic flight speed, the increasing pressure rise accompanying higher flight speed renders the ramjet most suitable for supersonic or most efficient at speed around Mach 3 or so. So, it has some, let us say, advantage and some disadvantages. Let us look at it. Able to attain high speeds, that is around Mach 5, no moving parts, so less wear and tear as well as minimum losses, reduced weight plus smaller engine size. Then you have lighter and simpler than turbine based engines. You have higher temperature can be employed. So, these are some of the notable advantages, but obviously every advantage comes with some sort of a disadvantage. So, at low speed, poor performance, so that is one. So, it needs booster to accelerate the speed, needs booster to accelerate the speeds, where ramjet starts to produce thrust. Then higher fuel consumption, then maximum operating altitude is also limited, then high temperature material is required. So, this is what it needs. So, these are now some of the advantage and disadvantages of ramjet. Then the other thing is that one can look at where the applications are. One of the important application is that missiles. Okay. So, it can be used in missiles for let us say it could have air to air missiles, then it could be air to surface missile, then air to air missiles, it can enable medium range missiles to maintain higher average speed. For example, MBDA Meteor, others are AIM-120, AMRAAM, like that, Gorgon 4. Air to surface, these are the examples like IDS, ASAP, Mosquito, something like that. Then you can have also you can have air to ground missile like by Mirage 4 or Mirage 2000, liquid fuel ramjet 2, capability range 20 kilometer. Then you have surface to air missile, again the examples like MBDA, LFKNG, these are for US based. Then you can have anti-ship missile, which are again where. So, these are different missiles application. Then you can have aircraft applications. Okay. So, variant of pure ramjet is coupled to other type of engine like piston or turbojet or turbofan to power the aircraft. Then one could be example of which we have seen the Leduc 1 or the Nord 1500 Griffon. So, these are the one which are coupled with the thing, and then others countries like German, Japan, they also have these things, Soviet Union and all this. So, there are two primarily kind of application. One is the missile applications where this is very handy, other applications of these aircraft applications when it could be coupled with the. Now, we can look at the cycle analysis. For cycle analysis or thermodynamical analysis, we have different modules. Let us see the first the intake module. So, intake module looks like this is how the intake module looks like, and this goes like this. So, here you have internal compression, here you have external compression, where you can see there could be shock waves, oblique shock, and there could be a lot of cross shocks which will form here like this. So, this is an intake module is quite important in the sense this does not have any rotating part. So, the intake actually does the compression process for this. So, it could have different shape, or it could be also having a constant, or it can may be constant or variable area duct. Okay. So, also it has the supersonic one has some spike which allows this kind of shock interaction to take place. So, what we can look at. So, now if you see this one, and let us say this is a station at which is A, and this is a station at somewhere at B, then the TS diagram would look like the TS diagram. So, this is what I am here going there. So, like this. So, that is point A, that is point, let us say B, and so this is B, and this is 0A. So, this is 0BS. Now, we have this temperature is T naught A, which is T naught B. This temperature is T naught BS. Then we have this portion which is completely V A square by 2 C P. This is T A. So, that is how the TS diagram would look like. So, what one can write, the isentropic efficiency is for the intake T B naught S minus T A by T naught B minus T A, where T naught B by T A is T naught A by T A, which is 1 plus gamma A minus 1 by 2 m A square, and P naught B by P A 1 plus eta I gamma A by 2 m A square to the power gamma A by gamma A minus 1, where the static temperature are T P and the total condition is all with the naught. So, that is how you can look at the intake module. And now, we can see the second module is the combustion chamber or burner. So, this we can see a sort of an diagram the combustion chamber could be where this is, you have intake. Now you have eta I, pi I. So, pi I is the pressure ratio, you got input M A, you got T naught B, you got P naught B, and you have T A, you got P A. So, that is what happened in the intake. Now, what happens in the combustion chamber? Now, this is what is happening at the intake. That means what you give input, you get it. Now, the combustion chamber, let us say we have a sort of an combustion chamber like this, and the geometry of like that. So, I have this kind of things. So, let us say this is point A, this is A, this is the combustion chamber. So, this is drawn in a axisymmetric fashion just to show you. So, here the TS diagram for the combustion chamber. So, this portion is the combustion chamber. So, the TS diagram would show like this: A to B, so that is the delta P, this is A T naught A, and this is T naught B. So, there are 2 points where it happens. Again, we can use the first law of thermodynamics and continuity equation. Now, the block diagram for the combustion chamber could be like this. This is the burner, let us say. What comes in? T naught A, what goes out? P naught A, here m dot F, and this goes out T naught B, P naught B. And so, here A is, so every time inlet, B is outlet. Similarly, for the intake also we have used that kind of fashions. So, now here the and QHB, let us say heating value of fuel, and air mass flow rate, and the eta B is burner efficiency. So, what we can write like P O B equals to P naught A minus delta P B, and T O B would be m dot A C P C T naught A plus m dot A eta B Q H B C P H m dot A plus A. So, m dot A is the air flow rate, and the C P C is cold air specific heat, and the C P H is the hot air specific heat. So, that is how. So, first what we are going to look at like this different individual modules, we have looked at the intake, and then now looking at the burner. Similarly, we will look at the nozzle before moving into the complete set of complete engine analysis for the ramjet. So, we will look at these components like what we have done, then we move to the next one. So, just we will stop the discussion here and continue the discussion in the next class.